Spring block energy. We have a block of mass 0.15 kilogram resting on a frictionless table, and it's attached to a horizontal spring which is attached to the wall. The block undergoes simple harmonic motion. When it is 0.014 meters from its equilibrium position, a motion sensor measures its velocity at 0.35 meters per second. So find the total energy of the block, find the max displacement of the block, what is the magnitude of the maximum velocity of the object, and what is its displacement from the object from its equilibrium position, that's where x is equal to 0, and also find its velocity when its kinetic energy equals its potential energy. To find the total energy of the block, we know that it is shared between potential energy and kinetic. We're given a certain position, so we can find the potential energy, and we're also given the velocity from the motion sensor. So we just substitute in the numbers we got from our analysis. Okay, there's the spring constant, and there's its displacement, and at that displacement, this is its velocity, and here's its mass, and we go ahead and calculate it, and we get 3.4 times 10 to the minus 2 joules. Find the maximum displacement of the block from its equilibrium position. We make the statement that when it's at its maximum displacement, its velocity is 0. So all of its energy is elastic potential energy. And another name for maximum displacement is amplitude, which we represent by the letter A. So our total energy is all in potential energy at our maximum displacement point, which will be 1/2 Ka squared. So we solve that equation for A and find that A is equal to the square root of twice the total energy divided by K. We found the total energy in part A, we substitute the value in, and we find our max displacement is 0.016 meters. What is the magnitude of the maximum velocity of the object as it undergoes simple harmonic motion? When you're at maximum velocity, you have obviously maximum kinetic energy, but you have 0 elastic potential energy. So we can set our total energy equal to kinetic energy max, which is 1/2 mv squared max. And we solve now for V max, and we do the outer parts of this little equation here. And it's the square root of 2 total energy divided by the mass. We substitute in our numbers, and we found the total energy a couple slides ago, and we find our maximum velocity will be 0.67 meters per second. What is the displacement of the object from its equilibrium position and its velocity when its kinetic energy equals its potential energy? When the kinetic energy equals the potential energy, each must equal half of the total energy, right? Because they're equal, you add the two of them together, you get your total energy. So that allows us to solve either for the displacement or the velocity of the block for this special case. So here's what we're talking about right here. The two energies are equal, so each one shares the total energy equally. There you go. So we can say 1/2 kx squared is equal to 1/2 of the total energy. We rearrange that to solve for x, and we find that at position 0.012 meters, half of the energy is in kinetic energy and half is in potential energy. Now let's find the velocity there. Well, in that case, the kinetic energy is half the total energy. We solve for velocity, and we find that at this position here, x is equal to 0.012 meters. It has a velocity of 0.48 meters per second.